morning to all of you. Today we are going to discuss the process of filament winding, which is one of the important processes used for fabricating parts of polymer matrix composites. Just to take back into certain aspects which we have already covered, or just to revise or summarize what we have already covered in this particular module, we have already seen what are the basics of the materials. Like we have seen that the selection of materials is an important aspect. We have seen what are the factors that should be taken into account for selection of material for a particular application. We have seen the importance of polymer matrix composites in today's engineering application. Then we have seen some of the important processes which are used for processing of polymer matrix composites. We have seen the hand layup process, we have discussed the spray layup, we have seen the process details related to pultrusion, and we have also discussed the compression molding process. We have seen all these processes have got some specific application areas. We have also observed that they have got certain advantages and certain disadvantages vis-a-vis one another. In today's lecture, our focus is on filament winding. So, there are so many processes which are used for the processing of parts made up of polymer matrix composite, but if there are certain specific requirements, then filament winding is used. To start with, just let us see the name or the you can say title of the process, that is filament and winding. If you remember, in some of the previous lectures we have seen that the composite material or the polymer matrix composite is made up of a polymer which acts as the matrix, which is reinforced with the fibers. So, the fibers and the matrix, they combine together to make a composite material. So, we have different processes to combine the fiber and the resin, or the reinforcement and the matrix, or the fibrous reinforcement and the polymeric matrix. So, we have two important macro constituents which we combined together to make a composite material. So, if we talk of the matrix part, we can have polymer as the matrix, we can have ceramic as the matrix, and we can have metal as the matrix. But in our module, we are focusing on this particular module, module 5, we are focusing on processing of polymer matrix composites. So, no doubt there is the matrix will always be in the form of a polymer, and the reinforcement would always be in the form of certain fibers. Fibers may be continuous fibers, they may be discontinuous fibers, the fibers may be aligned in one particular direction, or they may be randomly oriented in the bulk of the matrix. So, the name suggests filament and winding. So, we have a filament. Filament is one form in which the fibers may exist. So, we have a fiber which is we are calling here as a filament. The filament is type of a fiber or the form of a fiber. So, we have a filament and it has to be wound over a particular mandrel in order to give it a shape. But only the winding of the fiber or the fibrous winding will not give us a composite material, because in composite, as I have already discussed, there are two important constituents which should be present. Now, what are these two important constituents? These important constituents is the reinforcement and the matrix. The reinforcement is always in the form of fibers, and the matrix provides the bulk, and it is a polymeric matrix. In this, that is the topic, or this is a particular module dedicated to polymeric matrix composite. So, in these discussions our matrix would always be a polymer or a polymeric matrix. So, when we have a fiber in the form of a filament and that we are winding over a mandrel, suppose this is my mandrel, and on this mandrel if I am winding the fiber, we can say it is filament winding, but the filament also has to have some matrix. Matrix means these individual filaments have to be coated or impregnated, maybe impregnated is the right word. These filaments have to be impregnated with the matrix. So, what is a matrix? The matrix actually is a polymer. So, the two things when combined together, that is the fiber and the matrix or the resin. The matrix and the resin is one and the same thing. The matrix is a more generic form and resin is one type of a matrix. So, when we have a resin and we have a fiber, and when we combine them together we get a composite. So, fiber in case of filament winding would be existing in the form of a filament, and the matrix would again be a polymer. So, we can have thermoset polymer, we can have thermosetting polymer. We have seen that the polymers are also categorized into different categories, and two broad categories of polymers are the thermosetting polymers and the thermoplastic polymers. So, today we will see that how the filaments will get impregnated, how they will be wound, and how we will get a product by the process of filament winding. So, we have already seen there are number of processes which have been already discussed, and we have seen that each process has got its advantages, each process has got its limitation, and each process has got certain specific application areas. So, we will see filament winding, what are the specific requirements or what are the specific types of the filament winding or specific areas of application of the filament winding process. We would also see that which are the important control variables in the filament winding process, and finally the advantages, limitations and the specific application areas of the filament winding process we would be seeing in the subsequent slides. Now, the important question before we go to the discussion about the filament winding process, how to easily produce axis symmetric solid and hollow composite parts. So, we have a axis of symmetry and we have a, you can say, a hollow or a solid cylindrical or you can say axisymmetric part. So, suppose I have to make a hollow cylinder or I have to make a solid cylinder, and the material is a fiber reinforced plastics or for that matter a polymer matrix composite. So, if I have to make a solid or a hollow cylinder or any axisymmetric job in which I will have fiber and the matrix, the process that we are going to choose is the process of filament winding. That is the limitation of hand layup, spray layup and compression molding. So, when we have to make an axisymmetric component, it is difficult to process using the hand layup process or the spray layup process or the compression molding process. So, these three processes as you see on your screen have the limitation that they are not much suitable for making a axisymmetric component out of a composite material. So, it is difficult with these processes to make a axisymmetric component. So, axisymmetric components can be made by the filament winding process. So, on your screen you can see the solution of the limitations of the processes that we have already discussed is the filament winding process. So, today we will see the basic procedure or the basic sequence of operations in the filament winding process, the important control variables in the filament winding process. As I have already told, as we have been discussing in the previous lectures also, our focus would be on the advantages, limitations and the application areas of the filament winding process. Now, this diagram again and again I am referring to in each and every lecture, because this is relevant to the classification of the processes which are used for making the polymeric matrix composites. So, we can see in processing of polymeric matrix composites, we have three different types of processes: the open mold processes, the closed mold processes and the others. In others we have pultrusion and filament winding. In these series of lectures in module 5 on processing of polymeric matrix composites, we have already seen the hand layup process, the process itself, the process details, the control variables, the advantages, limitations and applications of the hand layup process. Similarly, for the spray layup process, which has already been covered. We have also seen the process of pultrusion, that what are the application areas of pultrusion and what type of composite products can be made by the process of pultrusion has already been covered. We have also seen compression molding in the previous lecture, that what is compression molding, what are the important or the critical parameters which have to be taken care of when we are processing the polymeric matrix composites using the compression molding process, that has already been covered. So, in today's lecture our focus would be on the filament winding process, which falls under the others category of processing of PMCs. Now, the filament winding process. Filament winding process is used for the production of composite products with high fiber volume fraction and controlled fiber orientation. So, there are two important points in this particular highlight or the bullet, that is filament winding is used for production of composite parts, that is obvious, because we are discussing it under the module 5, which is for processing of polymer matrix composite. But the important point to note in this particular point is the high fiber volume fraction which can be achieved in the filament winding process, and secondly the controlled fiber orientation. Now, the controlled fiber orientation is very important from the properties of the composite product point of view. The mechanical properties of the final composite product which we are making out of the filament winding process will depend upon the fiber volume fraction. When we are designing a particular component or a part which has to be made by the composite material using the filament winding process, two of the important points would be the fiber volume fraction and the fiber orientation, because the mechanical properties would depend on the fiber orientation. Now, suppose I have the fibers in one particular direction. So, let us try to understand the importance of fiber orientation in the properties of the composite products. So, on your screen you can see, just try to understand that suppose this is a simple composite part and we have all the fibers in one particular direction. Now, suppose we have, and I blow up this particular area. If I look it from this side, I have the fibers ends like this. So, these are the fiber ends, and in between we have got the matrix material. The dark portion is the matrix material and we have fiber ends. Now, if this particular component is loaded, suppose in the under compressive loading, so the compressive strength in this particular direction, that is along the fibers, would be different than across the fibers. Similarly, if we load this particular component under tensile loading, the tensile strength in the direction of the fibers would be higher than the tensile strength across the direction of the fibers, because this is the direction of the fibers. Again I am highlighting, this is the direction of the fibers, all the fibers are in this particular direction. So, depending upon the fiber, and this is called the fiber orientation. Now, suppose this is my axis x and this is my axis y. So, x and y axis we have the fiber orientation in this direction. So, this can be treated at 0 degree. So, all the fibers are oriented as 0 degree. So, fiber orientation plays a very important role in case of polymer matrix composites, and in case of filament winding we are able to control this fiber orientation in our final product. As we have already seen that in case of axisymmetric components made by the filament winding process, we can easily control the fiber orientation. Now, let me show a simple cylindrical component. On your screen you can see we have a component like this. If I see it from this side, it is cross section is circular in nature. So, we can have a control over the fiber orientation. All the fibers can be oriented in this fashion, and similarly they can be oriented in this fashion in the next layer. So, we can control the fiber orientation, and this particular fiber orientation will dictate the properties of the composite material. So, this is nothing but what has been highlighted in the slide as the fiber orientation. So, all the fibers are oriented in one particular pattern. So, this is also called as the winding pattern. So, we can alter the winding pattern and we can properly dictate the properties of the filament wound composite product. So, in this particular process of filament winding, fiber orientation is a very important critical parameter which has to be taken into account while designing the composite product or the part which has to be made by the filament winding process. So, we can also see that if suppose all the fibers are in one particular direction. Now, this is again a part which has a circular cross section. So, if we have all the fibers like this and it is loaded in this particular direction, we will not get very high strength. So, it may fail at a very low value of the loading. So, if we have fibers wound at the different angles like this and fibers wound like this, the component will have higher strength as compared to the fibers wound earlier. So, we have to see that how the filaments are going to be wound over the mandrel. So, we are still to understand the basic process of filament winding, but before going to the process details, we should understand that what do we mean by fiber orientation, what do we mean by winding pattern, because these are the things that would be coming up in discussion when we will discuss the details of the filament winding process. So, in this particular explanation, I have tried to emphasize the importance of fiber orientation, because this is important in terms of the filament winding process. Now, let us see the procedure of the filament winding process, that how the process actually takes place. So, on your screen you can see the filament winding process is used for production of composite products with high fiber volume fraction, which we have already seen that what do we mean by the fiber volume fraction, and controlled fiber orientation, which I have explained just now that the fiber orientation has a very important role or is of great significance because it dictates the final mechanical properties of the part made by the composite material. So, it is a composite processing technique in which resin impregnated fibers are wound over a rotating mandrel at the specific orientation. So, it is a very, you can say, it is simple to understand process in which a fiber or a filament gets impregnated in the resin bath and then it is wound over the rotating mandrel and the fiber orientation can be controlled easily. The process is suitable for production of composite parts in cylindrical structure. So, this is one particular application of the filament winding process in which the production of cylindrical structures or production of axisymmetric components such as cylinders can be achieved. Cores may be used in the method, but normally product is in single skin. So, we can have the cores, as the cores is a very common term in casting. The cores can also be used in making the composite products, but usually these filament wound products are produced in the single skin mode only, that it will be have a uniform thickness and cores may not be used in the filament wound products. Nowadays, computer controlled machines are used which independently monitor every movement of the whole process, resulting in production of complex geometries. So, earlier when this process was designed, it was developed, it was used for axisymmetry component, and the complex geometry of the axisymmetry components was sometimes a hindrance in the application of the filament winding process. But with the development of sophisticated computer numerical control machines and with the help of certain further design guidelines or design modifications which have been noted, and with the development of new materials which are used for making the mandrel, now this process can achieve fairly complex geometries. Also, the process is suitable from small to large area products in which high to low volume production can be there. So, filament winding process can be used for low volume production also, it can be used for high volume production also, but as the experimental setup or as the machine has got a high infrastructural cost associated with it, it is always suggested that it should be used for a high volume production products, and it is suitable from small products to the large products. So, very large products can be made. So, if we just talk about the size of the composite products which can be made by the various processes and compare the various processes, we can see that hand layup and spray layup process can be used for very large products. On the other hand, filament winding process can also be used from low to large size of the product, or from smaller to large size of the products. But on the contrary, compression molding can be used for low to medium size of the products, and pultrusion process can be used for continuous products, but the cross section should also not be very large. So, depending upon the size of the product, we can choose a particular process for a particular application. So, filament winding process can be used for small products also, it can be used for large products also. and the volume of production can be low as well as it can be high, but it is suggested that it should be used for high volume production products only. Well known and established process for thermosetting polymers. So, this is a well established process specifically for thermosetting polymers. Now, coming on to the raw materials which are used for making composite products, as we have already discussed in our previous lectures, that the raw material is in the two forms. One is the reinforcement and another one is the matrix. So, reinforcement and matrix combine together to make a composite material. So, we have to provide a reinforcement here and we have to provide a matrix here, and these two things when they combine together they make a composite product, and the filament winding process facilitates the combination of the fiber and the matrix. So, what type of reinforcements can be used in the filament winding process? On your screen you can see what are the different types of reinforcing materials. We can use glass fibers, either E-glass or S-glass, structural glass, or we can have carbon fibers, we can use aramid fibers. So, different types of synthetic fibers can be used for the filament winding process. Fibers are in the form of a straight filament coming directly from the creel, and it can be a kind of woven mats are not used in filament winding. It cannot be kind of woven mats are not suitable for filament winding. Some machines may be developed specifically for using the woven mats, but in general purpose filament winding machines we are going to use fiber in the form of filaments only, which would be wound on the mandrel for making a composite product. So, reinforcing materials are, once again to revise, we can have glass fiber either E type or S type, we can have carbon fiber, we can have aramid fibers. Fibers have to be in the form of straight filament which is coming from the creel. Woven mats are not suitable for filament winding process. So, reinforcement should not be in the type of the woven mats. Now, what type of matrix materials can be used? So, matrix can be either a epoxy matrix, it can be a polymer matrix, we can use polyvinyl ester, phenolic resin. So, there are different types of matrices like epoxy, polyester, polyvinyl ester, phenolic resin, and these type of matrices would be used in the resin bath, and these resins would be used in the resin bath. The fibers would be impregnated and finally wound over the rotating mandrel, and finally we can control the winding pattern and the fiber orientation whatsoever we want to call. Now, in filament winding process, fiber strands are unwound from the creels and they are passed continuously to the resin tank. So, let us first see theoretically that how the process looks like and how the process takes place, and then we will try to understand it with the help of a diagram. So, in a filament winding process, as in the case of pultrusion process, we have the fiber rovings which were placed on the creels and the fibers were coming and they were getting impregnated in the resin bath. The matrix, or you can say the polymer, was in the form of a resin which was put in the resin bath, and the fibers got wet through the resin bath and finally they were put into the preformer and then forced into the die and pulled by the pulling mechanism on the other side of the die in case of pultrusion. But in case of filament winding, the fibers are again coming in the form of filament from the rovings or the creels, and then these particular fibers are getting impregnated in the resin bath. So, there are two things which have to be there in order to make a composite, a reinforcement and a resin. So, the reinforcement is in the form of the fibers, which in this particular case we are using as the filament, and then the resin is acting as the matrix. The resin is available in the resin bath, the fibers are coming, they are getting impregnated in the resin bath. So, now we have the raw material ready. We have the reinforcement in terms of fibers, we have the matrix in terms of resin. So, the reinforcement and the matrix, when they combine together, they make a composite material. So, now my raw material is ready, the fibers are there and the resin is there, and the fiber is getting impregnated in the resin, and the raw material is now ready for the final deformation. I should not call the word deformation, but for the final winding on the mandrel, or the final you can say processing into the composite product. So, I have in a way, using the process, been able to combine the two things together, that is the fibers are coming from the creels in the form of filaments and they are getting impregnated in the resin bath. So, the raw material is now getting ready, and now when this raw material is getting ready, it has to be wound over the mandrel, and the mandrel is also rotating. So the load or there has to be adequate fiber tension so that the rolling takes place or the winding takes place over the rotating mandrel. So here we can see in the very first point on your screen, I am again reading it for you. Let us revise. In filament winding method, fiber strands are unwound from the creels. So the fibers are wound over the creels, and when we are making a composite product, the fibers would be unwound from the creels and passed continuously to the resin tank. So they are getting impregnated in the resin tank. In the resin tank, the fiber strands are impregnated completely with the resin. So the fiber strands will pick the resin from the resin tank. Resin impregnated strands are passed on to the rotating mandrel. The resin impregnated strands. Now the raw material is ready. We have the strands or the filaments and we have the resin. So resin impregnated strands are passed on to the rotating mandrel. So one thing is important to keep in mind, that the mandrel is rotating and it is causing a tension in the fiber, so that the fibers are pulled and they are getting wound over the rotating mandrel. Strands are wound around the mandrel in a controlled manner and in a specific fiber orientation. So the strands are wound around the mandrel. So mandrel is rotating, it is pulling, in a way it is pulling the fibers from the creels once the process has started. Now the mandrel is continuously rotating and the fiber is getting wound. Now how to achieve this directional fiber orientation and how to achieve this fiber orientation? This will be achieved with the help of a carriage that we will see in the process when we will see the actual diagram of the process. Curing of the composite, that is the process of solidification of the composite, is done with heat. So we can have heating arrangement around the filament wound product, generally in an oven, and the final composite product is taken out of the mandrel. So we have to then finally take out the composite product from the mandrel. Now suppose this is a mandrel and I have wound the filaments or the fibers over this particular mandrel. Ultimately I have got the length over the mandrel and I have got certain thickness over the mandrel. Now my composite product is on the top of the mandrel. Now finally this mandrel has to be taken out in order to get the hollow composite product. So finally the mandrel would be removed and we will get the final composite product. Now the important point to note is that the mandrel should easily be extracted from the composite product which has been wound over the mandrel. So the extraction of mandrel is also equally important, and this also gives us an idea to select appropriate material for making the mandrel. Sometimes we may make a mandrel out of a material which has a low melting point, so that once the composite product is ready, when we heat the composite product for the curing process, the mandrel should automatically melt and come out. Also sometimes we may suggest the use of collapsible mandrels, that once the process is complete, the composite has cured and it has become completely solid, we can trigger the collapse of the mandrel and finally the extraction of the mandrel from the composite product becomes easier. So the curing of the composite is done with heat, generally in an oven, and finally composite product is taken out of the mandrel. I have given few ideas that how the mandrel should be chosen so that the extraction of the composite product becomes easier. To remove the metallic mandrel from the composite part, hydraulic rams may be used, which is another area or another important way of removing the mandrel from the composite product. For complex geometry of composite part, the mandrel used may be soluble plaster which can be washed out after processing. So one other type of mandrel material is suggested here which will help us in order to easily remove the mandrel from the composite product, because here the composite has been wound over the mandrel. So the mandrel has to be removed later on in order to get the final composite product. So how the mandrel can be removed? There are 2-3 points which have been highlighted here which will help us to extract the composite product and to remove the mandrel on which the final product has been wound. Mandrel material may be collapsible rubber or materials having low melting point, which I have already highlighted that it can be a collapsible material also, that once the filament wound product is ready over the mandrel may collapse and it may be taken out easily, and the product is already solidified, it is in the form in which we have designed or we have required. So, it can be later on used or can be put to the specific application. The profile of the mandrel is exactly the same as that of the final product required. Now, depending upon the shape of the mandrel, we will get the final, we can control the inner cross sectional area of the final filament wound product. We can have different shapes of the mandrel because on top of the mandrel the filament winding is taking place, or the product is being made on top of the mandrel. So, the inner details of the product, if we want to have certain specific details, we can design the mandrel accordingly, and on that particular shape of the mandrel we will do the winding, and later on the mandrel would be taken out and the final product would be ready. So, the profile of the mandrel is exactly the same as that of the final product required. So, the two things should match, and specifically it is important that we are able to control the inner, we can say, geometry of the final product. In some cases mandrel becomes the integral part of the assembly. Sometimes it may so happen that we do not require to remove, or it is not an requirement to remove the mandrel, it has to be a solid product. So, the mandrel will become a part of the final product. So, we have a inner core which is a mandrel, and on that core we are doing the filament winding. So, on the outer periphery we have the polymer matrix composites or the fiber reinforced plastic, and inner we have a core which is a mandrel. Now, the core material can be metallic, it can be other type of plastic, or it can be rubber. So, the mandrel can be of any material, but it will become an integral part of the final product. So, in this particular scenario we need not remove the mandrel out of the composite product, it would become a part of the final product. So, inner core will be a mandrel and the outer periphery would be the fiber reinforced plastic or the polymer matrix composite which has been wound over the core. A carriage is used to keep the rovings in place and to direct them to the mandrel. So, the fibers are controlled by the carriage, and the final supply to the mandrel is through the carriage, which we will try to understand with the help of a diagram. On your screen you can see a very simplistic representation of the filament winding process. If we are able to understand this, we will be able to design a filament winding setup on our own. There are few critical parameters which have to be taken into account that we would be seeing in the subsequent slides. So, you can see here these are the fiber creels on which we have the raw material in the form of the fibers. So, the fibers are coming, individual fibers are coming, or we can say this is the fiber roving. From the fiber rovings we are getting the fibers, and this is the resin tank where we have the polymer. So, the reinforcement is in the terms of the fibers and the resin is acting as the matrix. So, we have a reinforcement, we have a matrix, and finally we have to develop a composite material. Now, this is the rotating mandrel. So, this rotating mandrel is rotating. Here we can see the rotation of the mandrel has been shown. So, the mandrel is continuously rotating. The fibers are coming from the creels and they are getting impregnated in the resin bath. So, this is resin impregnation of the fibers, and finally they are moving out after getting impregnated, or here they carry the resin with them. From these creels, when the fibers are coming, they are dry fibers. When they get impregnated with resin, now they are having the resin and the fiber. Now, the fibers are carrying the resin with them in this particular area, and when these resin impregnated fibers they move through the eye of the carriage, this we can call as the eye of the carriage. This is our total carriage, and this is having a linear movement along the axis of the rotating mandrel. Now, this is the rotating mandrel and this is the axis of rotation. So, this particular carriage is having a linear movement parallel to the axis of the, or in the direction of the axis of the rotating mandrel. So, this linear movement would help us to control this fiber orientation. Here you can see the fibers are in this direction also and the fibers are in this direction also. So, this is called the winding pattern, which I have explained in the previous slides. I have explained that the fiber orientation has got a very important role to play in the mechanical properties of the final product. So, on your screen you can see we have a specific winding pattern. So, with the proper design we can control the winding pattern, that how the winding of the filaments would take place or the fibers would take place on the rotating mandrel. So, this is called a carriage and the carriage will have a linear movement. So, this winding pattern basically will depend upon two movements. One is the rotation of the mandrel and another one is the linear movement of the carriage. So, if we are able to put an optimal combination of the rotation of the mandrel and the linear movement of the carriage, we would be able to generate a winding pattern which would result in very good mechanical properties of the filament wound product. So, basically there are two important things that we need to control here, that is the speed at which or the RPM at which the mandrel is rotating and the movement of the carriage, that is the speed at which the carriage is moving. So, we now need to have control over the two important movements that are there in this particular diagram, that is the movement of the carriage and the rotation of the mandrel, and a proper, we can say, important combination has to be designed or developed between the rotational speed and the linear movement of the carriage in order to develop a very good winding pattern in case of a filament wound composite product. If we get a good winding pattern and a good fiber orientation in different layers of the composite product or the filament wound product, the final properties of the mechanical properties of the final product which has been made by the filament winding process would be suitable to our requirement. So, we need to understand that these are the two important things, that is the winding pattern which further depends upon the rotating speed of the mandrel or the RPM of the mandrel and the linear movement of the carriage. So, there are few critical parameters that we have to take into account when we are discussing the filament winding process. So, the main component of the setup or the filament winding machine are the fiber creels from which the fibers are coming, the resin impregnation system where the fibers are getting impregnated with the resin, the carriage which is having a linear movement and which is the final, you can say, point from where the fiber is going towards the mandrel or the rotating mandrel and the rotating mandrel. So, we have seen that the rotating mandrel is also equally important. We have to see the geometry of the rotating mandrel, we have to see the material out of which the rotating mandrel is made, and we have to control the speed of the carriage, that the linear motion of the carriage has to be controlled. So, these are the few important points or few important elements of the filament winding setup. Now, what are the controlling parameters? So, there are few important controlling parameters in the filament winding process. So, these are the fiber tension. The fiber should have adequate tension. If they are you can say pulled very quickly or they are pulled at a very slow pace, it would affect the properties of the final product. And if they are under very high tension, it may result in the final fracture of the fibers also. So, there has to be a optimal and the adequate value of the fiber tension. It should not be very high, it should not be very less, because the consolidation process, now we have seen in some of the previous processes, let me highlight the word consolidation. In some of the previous processes we have seen, like in hand layer process, how the consolidation is taking place. We have two plates and we are applying the pressure on the top plate and we are doing the layup on the bottom plate and applying the pressure with the nuts and the bolts assembly, or we can have additional static load on the flat plate mold. So, the consolidation is taking place by the application of pressure or load. In case of spray layer, we are using a consolidation roller to consolidate the composite product. In case of pultrusion in the die, we are having you can say controlled temperature and curing is taking place, the cured product is coming out, the consolidation process is taking place within the die. In case of compression molding, we are having a combination of the pressure and the temperature and the consolidation of the product is taking place. But in case of filament winding, the consolidation will depend upon the fiber tension. So, if we have adequate tension, optimal tension, it should not be very high, it should not be very low. So, if we have optimal tension in the fibers when they are getting wound over the rotating mandrel, we will get very good consolidation of the final product. So, fiber tension is a critical parameter, and we would be discussing maybe 1 or 2 more slides on fiber tension. We have the winding speed, or we can say this is the speed at which the mandrel is rotating. The design of the resin bath, how the fibers are getting impregnated. So, that is also equally important. If all the fibers do not get wet, the final product that we will be getting would not be of the adequate properties and may fail when it put to use. So, that we have to design the resin bath in such a way that each and every fiber should get wet when it is passing through the resin bath. Viscosity of the resin is also equally important. Winding pattern, as I have already explained, that the fiber orientation plays a significant role in dictating the mechanical properties of the filament wound products. So, we have to see that we attain a very optimal winding pattern, so that the properties are as per our requirement, and the carriage movement has to be controlled, because we cannot have a too fast carriage movement or a too slow carriage movement. And if we have a proper relationship between the speed of the rotating mandrel and the linear movement of the carriage, we can dictate or we can control the angle of fiber orientation. So, we have to control the carriage movement, we have to control the winding speed, we have to control the viscosity of the resin, we have to control the winding pattern, and most importantly the fiber tension. So, let us see how the fiber tension plays an important role in the consolidation process. So, fiber tension is critical in filament winding because compaction is achieved through the fiber tension only. So, the important point, the consolidation word has been replaced by compaction. So, the filament wound product would be very compact, it would be consolidated if we have a adequate fiber tension. The fiber tension affects the percentage of fiber reinforcement and porosity content in the composite, which in turn affect the properties of the processed composite product. As I have already explained, the mechanical properties would certainly depend upon the fiber tension, and the fiber tension would further dictate the fiber volume fraction that is present, or the percentage of fiber reinforcement in the final product. So, if we have the fibers coming loosely and they are not getting wound properly on the rotating mandrel, the fiber volume fraction would be less and too much of resin will be there in the final product. But if we have adequate tension of the fiber, we will get a consolidation and we will get a very compact filament wound product. So, the fiber tension affects the percentage of the fiber as well as the porosity and void content in the filament wound product. So, we have to appropriately and judiciously select the fiber tension during the filament winding process. The fiber tension depends upon the type of the fiber, the geometry and the winding pattern required on the rotating mandrel. So, we have to judiciously and we have to very intelligently select the type of fiber, and on that type of fiber the fiber tension will depend. There may be some fibers, if you apply lot of tension on them, the fibers may break also, and then these type of reinforcements are not suitable for making composite products by the filament winding process. So, we have to choose the type of fibers in such a way that we can have a adequate level of tension during the process. So, fiber tension is very important. So, if there are some fibers which cannot take that much of tension, they have to be discarded for filament winding process, means the filament winding process is not suitable for making products by those type of fibers which cannot take the adequate amount of tension. So, the fiber tension, again to revise, depends upon the type of the fiber. We have to choose those fibers only which can take the tension and its geometry as well as the winding pattern required on the rotating mandrel. So, the winding pattern required is also very important. The fiber tension should be an optimal level, because too high fiber tension may break the fiber completely or initiate fiber fracture at the surface. So, I have already highlighted, I have already explained that too high fiber tension is also not desirable, because it may lead to the fiber fracture or the failure of the fiber before the actual winding process, or the surface of the fiber may get degraded because of very high tension. So, we have to judiciously and optimally select the fiber tension during the filament winding process. So, we have seen that there are few control variables in the filament winding process which have to be taken care of. Now, just to revise that, what are these important points or critical parameters which should be taken into account while we are discussing the filament winding process. Now, these are the rotational speed or the winding speed, that is the RPM of the mandrel, the linear movement of the carriage, the tension in the fiber, the resin impregnation system. So, these are 3 or 4 important critical parameters which should be taken into account while discussing the filament winding process, because if any one of these parameters is not taken care of or is not given due importance and attention, then the final product that we are getting using the filament winding process may not be of a very high quality. So, if for making a good quality product, we have to select the rotation speed, we have to select the translation or the linear motion of the carriage, we have to select the appropriate resin system and the resin impregnation system, and we have to provide adequate type of the fiber, and the fiber tension should be optimal, so that we get a very good quality product. Now, what are the advantages of the filament winding process? So, we have been discussing the advantages and limitations of some of the processes like the hand layup, the spray layup, compression molding, pultrusion. So, vis-a-vis other processes, filament winding has got certain advantages and it has got certain limitations also. Now, we are going to discuss the advantages of the filament winding process. High strength to weight ratio is possible to achieve with this process, because the fiber volume fraction or the percentage of fibers in the final product is high. Therefore, we are able to achieve high strength to weight ratio with the filament wound products. High degree of uniformity in fiber distribution, orientation and placement, because here we are having a continuous fibrous reinforcement, we are able to control the uniformity in fiber distribution, and orientation and placement is also good in the filament winding process. So, the orientation and placement is in context of the fibers. The fibers orientation and the placement of the fibers in the matrix is optimally controlled in case of the filament wound products. Labor involvement is minimal as it is a automated process. So, it is very clear that it is an automatic process, so the labor involvement is less. Filament winding method is suitable to process composite parts requiring precise tolerances. So, for highly accurate and precise products, filament winding process is suitable. So, we can see that high fiber volume fraction can be achieved, strength to weight ratio of the products made by the filament winding process is very good, uniformity in fiber distribution, fiber orientation can be achieved by the filament winding process. So, there are certain advantages which are not available with the other processes which we have discussed till now. So, fiber orientation in a specific direction is possible in this process, as we have seen that the winding pattern will depend upon the rotational speed of the mandrel and the linear movement of the carriage. So, we can dictate the fiber orientation in the filament wound product. Design flexibility in composite part is possible with the change in the winding pattern, materials and the curing options. So, it is a versatile process, we can choose the raw materials, we can dictate or design the winding patterns, and we can adequately choose the curing options. So, because of all these options available with the engineers, the filament winding process can be used for a variety of composite products. The size of the composite component is not restricted. So, a large size component can also be made and a smaller size component can also be made by the filament winding process. For high production volume, process automation results in cost saving. So, as we have already seen that the filament winding process can be used for high volume production, it can be used for low volume production also, but for high volume, if we have a fully automatic process, it would lead to cost cutting or cost saving. Cost of the composite part processed through filament winding method is substantially low as compared to other manufacturing methods, as this process involves less and low cost materials to produce high strength component. So, the strength comes by the fibers, and we have already seen that in case of filament winding process, the fiber volume fraction that can be achieved is considerably higher. So, when we have higher fiber volume fraction, we will definitely get higher strength. So, the type of materials that we are using can be slightly, we can say, on the inexpensive side. So, instead of using very expensive materials to get a certain degree of strength, even if we are using slightly inexpensive material, but because of a very high fiber volume fraction which is achievable by this process, we can think of using certain materials which would reduce the cost of the composite product. Now, what are the disadvantages of the filament winding process? Capital investment is relatively high because we have to procure a filament winding machine. So, the capital investment is therefore relatively high. Very precise control of the mechanism is required for uniform distribution and orientation of fiber. So, this is one of the advantages that we can have a control, but in order to exercise this control, sometimes it may become difficult because it will depend upon the viscosity of the resin that we are using, it will depend upon the fiber tension, it will depend upon a number of other parameters. So, the precise control of the process is also equally important. So, if we are not able to precisely control the process, then it will become one of the disadvantages of the filament winding process. Composite product configuration should be such that it facilitates in mandrel extraction. So, if it is a very complex geometry, we may not be able to process it using the filament winding because the final mandrel extraction is one of the limitations. So, if it is a complex geometry, we are not able to extract the mandrel out of the filament wound product, then it becomes the one of its limitations. It is not possible to produce the reverse curvature. Yes, the outside curvature can be made, but if the reverse curvature has to be made, it is sometimes difficult to achieve by the filament winding process. For some applications, mandrel may be expensive and surface of the composite part may not be satisfactory. So, we can control the inner surface finish because that would depend upon the surface finish of the mandrel, but sometimes it becomes difficult to control the outer surface finish of the filament wound product, and we cannot do any finishing operation on that. Suppose somebody may suggest that we can do the turning of the filament wound pipes. It is difficult because when we start the turning, the fibers come out of the matrix and the fiber pull out takes place, and the surface, instead of getting improved, it further deteriorates. So, surface finish is difficult to achieve, and sometimes the outer surface is difficult to control in case of the filament winding process. Fiber direction cannot be changed within one layer of the winding. So, we have different layers of winding, and in one particular layer of winding, the fiber direction would be uniform or it would be same. So, in one particular layer, we cannot change the direction of winding. So, fiber direction cannot be changed within one layer of winding. So, fiber direction cannot be changed within one, it means that it will remain constant. So, the fiber direction cannot be changed within one layer means the fiber direction will remain constant in one layer of the winding. So, finally, we come to the applications. So, the composite products like storage tanks, pipelines, vessels, gas cylinders, fishing rods, missile cases, rocket motor cases, ducting, cement mixture, sailboat mast, aircraft fuselages and golf club shafts are commonly developed with this method. So, on your screen you can see a wide variety of products which are mostly axisymmetric in nature, and these can be processed by the filament winding process. Now, the application spectrum of filament winding has expanded to complex engineered non-spherical and non-cylindrical composite product with the use of sophisticated machinery and software. So, initially the application of filament winding process was only restricted to or limited to the axisymmetry components only, but with the development of new filament winding machines and with more degrees of freedom possible and with more sophisticated softwares that have come into place, now it has become possible to make different shapes of the products made by the filament winding process. So, the application spectrum of filament winding process has increased manifold over the last few years. So, there are large number of applications which you can see on your screen. So, in today's lecture we have seen the basic process of filament winding. With the help of the diagram we have tried to understand that how the filament winding process takes place. We have tried to highlight the critical factors which should be taken into account while operating the filament winding process. We have seen what are the advantages of the filament winding process, what are the limitations of the filament winding process, and finally on this particular slide we have seen that what are the application areas of the filament winding process. In the subsequent lectures in this module on processing of polymer matrix composites, we would be focusing our attention on some other processes such as resin transfer molding for the processing of polymer matrix composites. Thank you.